All right, so this is your turn. I want you to try to solve this problem based on the 3 equations that you've learned and using your calculator and applying those sig fig rules. The pH of urine may vary between 4.5 and 8.2. Calculate the hydronium and hydroxide concentration of a sample if the measured pH is 5.20. So I would really encourage you to pause the video and attempt to solve this yourself, and then look through it for the answer and further explanation. All right, so what is this question even asking you? So calculate these 2. So that's what it's asking. It's asking what is the hydronium ion concentration and what is the hydroxide ion concentration. So the moles per liter of that. And it has provided you with the pH. pH is 5.2. So we can't use pH equals negative log for this because we already know the pH. Instead, we want to use that other equation, which really isn't actually another equation. It is really just a different way of thinking about what a log base 10 value even is. The equation I'm referring to is this one. The hydronium ion concentration, brackets mean concentration, is equal to 10 raised to the negative pH power. And that's really what we mean when we're talking about logarithmic concentrations anyway. So by doing this, I should be able to then find the hydronium ion concentration, which is one of the things that I'm looking for. So I'll do that by taking 10 and raising it to the negative 5.20, to the negative pH. And that negative is important. If you get a really wonky number, that would be the first place I'd recommend to check. So let me show you me doing this on my calculator. Again, your calculator might be different. So I hit second log. So I'm not actually hitting the log button. Let me pause it for a second. You can see this yellow above this my log button says 10 to the x. So when I hit second and that, I'm really actually using that feature. So 10, and then my little caret. So it put that in for me. 10 to the, and then I'm going to put in negative 5.20. I leave the 0 off because it gives me that. So there's my value. You have 1, 2, 3, 4, 5, 6. So let me write that down so that I can remember it. We'll come back. We'll talk sig figs in a second. Another way to do that same thing is 10, and then I use the little caret because that means raised to the negative 5.2. And then I get the exact same value. So it doesn't matter which of those approaches you'd prefer to use or what you're comfortable with on your calculator, you should end up getting the same value. Now I'm not gonna reduce sig figs in the middle of a problem. However, this is one of my answers, so I am gonna get it up here. So but I do want to consider my sig fig values. And remember those really unique rules for sig figs. So in this case, when I'm starting with pH and I'm going to concentration, I look only at places past the decimal. And I have 2 places past the decimal for the pH. So that's what I'm going to do in total for my concentration. So my hydronium concentration, and I'm going to go ahead and write down up here, is 6 times 10 to the negative 6. And what are the units for concentration? Because pH is a unitless value. Well, it's moles per liter. So capital M or moles per liter. Now, what about hydroxide? So my hydroxide concentration is going to be found in the same way that I found that hydronium concentration in the problem that we previously did. I need to use the equilibrium constant for water and its equation. So the equilibrium constant for water is the product of the hydronium ion concentration and the hydroxide ion concentration, and it will always, at 25 degrees Celsius, equal this value. So if I want to solve for this, if this is my unknown, but I know this. I can put this in 6 times 10 to the negative 6. I actually like to go ahead and keep my sig figs in for these when I'm continuing calculating, and I can reassess sig figs. Every time you do rounding and sig fig stuff in the middle of a problem, you move the answer a little further from the true value. So the molarity of hydronium times my unknown, we'll just say x, should equal 1.0 times 10 to the negative 14. Whoops, I always forget that one. So, thinking algebraically, in order to solve for x, I need to divide both sides by the molarity because that makes it divide out. And what I get then is that the molarity of the hydroxide is equal to the Kw value, the ionization constant for water, divided by the hydronium ion concentration. And remember, as you've seen on previous videos, those parentheses, they're not really important on your page, but they are important depending on how your calculator works for doing those. And when I do that, I get a value of 1.6 times 10 to the negative 9. And again, moles per liter. So I think the last thing that you want to do in a problem like this, because this is our answer, this is what they asked us for, the hydronium ion concentration of this urine sample and the hydroxide ion concentration of this urine sample, is to kind of ask yourself, does that make sense? And the way I would approach it is like this. I look at the original pH. It's 5.2. Is that acidic or basic? Well, hopefully you said acidic because its pH is less than 7. So this is acidic urine. And why does that matter? Well, it gives us an idea about how the hydronium ion concentration should compare to the hydroxide ion concentration. In a neutral substance, these two should be equal. Not only should they be equal, but they would be 1.0 times 10 to the negative 7 each. That's only, though, if neutral. So the molarity of those two would be this, because those two multiply together to get that number, that if you're wondering where I'm getting that from. Since this is acidic, I know that the hydronium ion concentration should be greater. This is my greater than symbol, little Pac-Man. Greater than my hydroxide, which means it should be, this concentration should be larger than 1.0 times 10 to the negative 7. That means the hydronium ion is more common in this sample than in neutral pH 7 like water, and the hydroxide should be less. So this should be more concentrated than that in this sample, and this should be less concentrated than that. So let's see if that works out. So in my answer, I have 6.3 times 10 to the negative 6. Is that a bigger concentration than 1.0 times 10 to the negative 7? Yes, it is, by a little over 10 times. Now, I know that can seem weird because 7 is a bigger number, but remember, the 7s are the number of zeros in front. And if we just want to simplify it, you know, I think it's easy to see how the number of zeros definitely can make it. The more zeros, the smaller the value. So yes, smiley face. What about hydroxide? 1.6 times 10 to the negative 9. We predicted that the hydroxide value should be less, a lower concentration than at neutral, 1.0 times 10 to the negative 7. Is that what we found? Yes. 1.6 times 10 to the negative 9 is a lower concentration. The hydroxide is even rarer than we normally see in neutral water. So we can kind of stop and ask ourselves, circle around our smiley faces, like, does the answers that I'm getting in my calculations support what I know to be true about acids and bases? And what we know to be true about acids and bases is as the pH becomes more and more acidic, the hydronium ion concentration goes up from 1.0 times 10 to the negative 7, and the hydroxide ion concentration goes down. So as we decrease the pH of something, this is what happens. If we have it more basic, as the pH increases, We'd expect the opposite. We'd expect the hydronium ion concentration to be less and the hydroxide concentration to be more. So hopefully that makes sense and gives you some tools for checking your work.